Now, you hopefully remember that you've heard the term boundary value problem. So the first thing that I want to review is the difference between an initial value problem and a boundary value problem. So we've looked at both of these before. Let's say that we have some linear differential equation in standard form. So we have y double prime add p of x times y prime add q of x times y equals g of x. If this were an initial value problem, you would be given two initial conditions, y of x naught equal to y naught, and then y prime of x naught equal to y naught prime. So this is what we often see. Can't remember what section, but in some section we also saw boundary value problems. Same condition is the same, y of x naught equals y naught. Do you remember what the other condition is?
Y of x1.
Y of x1 equals y1. So with an initial value problem, you look at the derivative. With a boundary value problem, you look only at the solution. So this is called a 2-point boundary value problem because you're given 2 points. So today, and kind of for the rest of this unit, we're going to be looking at boundary value problems. Our goal is to find some y that's a function of x that satisfies the differential equation above for all x between x naught and x1 that takes on the values y naught and y1 at the endpoints of the interval. Generally, as we've always done, we're going to find the general solution first. So before we actually do any solving today, we're going to look at what could happen. So what kind of solutions could you have and when are those going to occur? And then we'll actually apply that. A new term, and by new term I mean it's kind of a new term. What's the term in differential equations that we use a lot to mean different things? Homogeneous. Lambda is a variable, yes, so we are going to use lambda. That will come up later, yes. Okay, a homogeneous boundary value problem is when y0 and y1 are both 0. Yes, that we're going to learn at least. I don't know if there are other meanings of it in differential equations, but this is the last one that we are going to.
Wait, so would they have different values at the end?
No, they're going to have the same value at the end.
That's
The same value of y.
That's what I tried to say.
Okay. Great. So now, like I said, we're going to look at what cases could occur. So we are going to consider a system of linear algebraic equations written as a matrix equation. Do you guys remember doing this at some point, like maybe algebra 2? You took a system of linear equations, you wrote it as a matrix, and it looked something like this: ax equals b. A being a matrix, x being a matrix, b being a matrix. A is all the constants, x would be your variables, and b would be kind of your answers. Okay, first let's consider the case where b does not equal 0, or does not equal the 0 matrix. If b does not equal the 0 matrix, then this would be non-homogeneous. or similar to a non-homogeneous boundary value problem. When this is the case, there are two cases that could occur. A could be non-singular, or A could be singular. If A is non-singular, it means it doesn't have an inverse, in which case we have a single unique solution. Bless you. If A is singular, then either we have no solution or infinitely many solutions. Okay, so a non-homogeneous boundary value problem is going to work the same way. If it's non-homogeneous, either there will be a unique solution or no solution or infinitely many. These two often come together, and you'll see what I mean by that in a little bit. We are also going to consider homogeneous boundary value problems, which would be the case when B is the zero matrix. If that's the case, our system then is AX equals 0, again, 0 being the zero matrix. Then X equals the zero matrix is always a solution. Oftentimes we're not interested in that solution though. That's the trivial solution. So again, two other cases arise. Either A is non-singular or A is singular. If A is non-singular, this is the only solution. If A is singular, there are infinitely many solutions. So this is way more interesting. If we have a homogeneous boundary value problem, we're never going to have a non-trivial unique solution. Either we're just going to have the zero, or we're going to have infinitely many solutions. Okay, so then linear homogeneous boundary value problems work in a similar way. Yes?
When you say only solution, do you mean that x is 0 is the only solution?
Correct. Okay, you do not need to memorize these cases, but they're going to help us when we solve the next few examples. So, first example, we have y double prime, add 2y equals 0. Our two boundaries are going to be y of 0 equals 1 and y of pi equals 0. Okay, first thing to notice is that this is non-homogeneous. If this then works the same way that matrices do, either we're going to have a unique solution, bless you, or the case of no solution or infinitely many solutions. The way to figure it out is to solve the equation. So what do we do in this case? The auxiliary equation. So we have m squared add 2 equals 0. M then is plus or minus square root of 2i. So then our y is going to be c1 cosine of root 2x plus c2 sine of root 2x. Looking at our first condition of y of 0 equals 1, we have 1 equals c1 plus 0, so c1 equals 1. Then if we look at y of pi equals 0. We get 0 equals cosine of root 2 pi plus c2 sine of root 2 pi. So if we move the cosine over and divide by sine, we get c2 is negative cotangent of root 2 pi. So our final solution then ends up being cosine of root 2x, subtract cotangent of root 2 pi, multiplied by sine of root 2x. So this is the case where we get a single unique solution. So this really shouldn't be anything too new, like this you've done before. Zach?
So did we just solve this? Like, what is the point of the whole matrix that we just talked about?
To show us what could occur,
Okay,
what
so
cases
we're
could
just
occur.
Okay.
So this is going to lead us to the next example we do. So again, if it's non-homogeneous, either we have a unique solution or no solution or infinitely many solutions. We just looked at the first case of a unique solution. Now we're going to look at a non-homogeneous equation where we have no solution or infinitely many solutions. This one is going to be y double prime add y equals 0. Our conditions are y of 0 equals 1 and y of pi equals a. So again, looking at the auxiliary equation, we get m squared plus 1 equals 0, m equals plus or minus I. So then y is equal to c1 cosine of x add c2 sine of x. Okay, again, we are going to have to look at the two conditions. If we look at y of 0 equals 1, we get 1 equals c1 again. Y of pi equals a. We get a equals cosine of pi plus c2 sine of pi. Now, sine of pi is 0, so we get a equals cosine of pi. Okay, here's where we have two different possibilities that can occur. First possibility is that we have no solution. Second case is we could have a is in fact equal to cosine of pi. So if a is anything other than -1, we have no solution. If a is in fact -1, then our solution is y equals cosine of x add c2 sine of x. So c2 is arbitrary. So this is that other possibility for a non-homogeneous matrix system, which is the same for a non-homogeneous boundary value problem. Either we have no solution or infinitely many solutions based on the value of a. Okay so far? So like I said, you don't really need to memorize those cases. It just shows you what could happen. We're going to do one more example and then we're going to go on. Next example we're going to do is similar to example 2, except we're going to make it homogeneous. So we have y double prime add y equals 0, y of 0 equals 0, and y of pi equals 0. So again, what makes this homogeneous is these two zeros right here. Anytime it's homogeneous, y equals 0 is automatically a solution. Now, that's either the only solution or there will be infinitely many. So we have to actually solve the equation to figure out which one's the case. We already did this. We know we get m to be plus or minus I. So our y ends up being c1 cosine of x plus c2 sine of x. Again, going to your conditions, y of 0 equals 0. This will give us 0 equals c1 plus c2 times 0. So c1 equals 0. Y of pi equals 0. We get 0 equals c2 sine of pi. Sine of pi we already know is 0, which means that c2 is arbitrary. So this would be the case where we have infinitely many solutions. Yeah.
So y of 0 isn't a solution then because we put down the other one?
So y0 is still a solution.
Oh.
And then this is the general
Just an
bigger.
extra,
Yeah.
Oh.
Okay, questions on boundary value problems before we go on to a special type of boundary value problem? Great. Next thing we need to talk about is eigenvalue problems. Okay, so eigenvalues you already know how to find from 8.4. You're not going to be finding eigenvalues in this section the same way you did before. Instead, we're going to be considering the following type of equation. Ax equals lambda x. Here, lambda being your eigenvalues. So there are two different solutions here. First solution would be that x is the 0 matrix. We already said that's trivial. We don't really care about that. We also have solutions at lambda, so at the eigenvalues. So we specifically are interested in finding the eigenvalues that will make this equation true. Okay, here's what we are going to be looking at this section. We're going to be looking at the differential equation or the boundary value problem, y double prime, add lambda y equals 0, with homogeneous conditions y of 0 equals 0 and y of pi equals 0. So this is similar to example 3 that we did above. Example 3, though, was the specific case of lambda being 1. So we already know that y equals 0 is going to be a solution. That's trivial. We don't care about that one. So we're specifically going to look for what values of lambda have a solution. So the values for which non-trivial solutions exist are the eigenvalues. So we're going to find the eigenvalues for which there are non-trivial solutions. The actual solution then is called the eigenfunction. There are 3 different cases that we need to consider. First case being that the eigenvalue is positive. In which case, what we're going to do is we are going to let the eigenvalue, so we're going to let lambda equal mu squared, just for convenience in solving. Because what we get then is we get y double prime add mu squared times y equals 0. Your auxiliary equation then will be m squared add mu squared equals 0. So m then is plus or minus I times mu. Our solution then is c1 cosine of mu x add c2 sine of mu x. First condition was that y of 0 equals 0. If we use that, we get 0 equals c1 plus c2 times 0. So we get c1 equals 0. we look at the second condition of y of pi equals 0, we get 0 equals c2 sine of mu times pi. Now, two cases. First case is that c2 could equal 0. If that's the case, then we end up with the trivial solution of y equals 0. We already said we're looking for the values for which we have non-trivial solutions. So if this is to be non-trivial, then we need sine of mu pi to be equal to 0. That will be the case if mu is 1, 2, 3, etc. We care, though, about the eigenvalues, so specifically about lambda. If lambda is equal to mu squared, that means our eigenvalues then, bless you, are 1, 4, 9, etc. So these are the eigenvalues. Our solution then is going to be of the form y equals c2 sine of mu x. We can choose whatever we want for c2, so I'm just going to choose c2 to be 1. So then some of the eigenfunctions will be y equals sine of x, y equals sine of 2x, y equals sine of 3x, etc. Those are all eigenfunctions, so all solutions for the given eigenvalues. You okay there?
Yeah.
Okay, we chose C2, or I chose C2 to be 1, so just remember that any constant multiples of these will also be solutions. So when C2 is another value, that will also work. Okay, second case is that our eigenvalues are negative. In which case we're going to let lambda be equal to negative mu squared. Again, just for convenience. So our equation then will become y double prime subtract mu squared times y equals 0. Our auxiliary equation will be m squared subtract mu squared equals 0. So m equals plus or minus mu. Our solution will then be of the form y equals c1 e to the mu x, add c2 e to the negative mu x. First condition was y of 0 equals 0. So we get 0 equals c1 plus c2. So c1 then is the opposite of c2. Next condition is that y of pi is equal to 0. We get 0 equals c1 e to the mu pi, add c2 e to the negative mu pi. So here's what I decided to do. I'm going to multiply by e to the mu pi. So then I end up with c e to the 2 mu pi plus c2. Now we know that c1 is equal to negative c2, so this becomes negative c2 e to the 2 mu pi plus c2. If I factor out a c2, I get negative e to the 2 mu pi plus 1. One possibility is that c2 would be equal to 0, which would also mean c1 equals 0, which would be a trivial solution then. Other possibility here, we could have 1 being equal to e to the 2 mu pi. If I take the natural log of both sides, I get 0 equals 2 mu pi, in which case mu would be equal to 0, which again would be trivial. That's not something that we're interested in. If that's the case, our equation would have just been y double prime equals 0. This tells us that the only solution is y equals 0. Here's what's important. We are looking for non-trivial solutions, which tells us we do not have to consider negative eigenvalues. So the negative eigenvalue only gave us trivial solutions that we don't care about. So positive eigenvalues we need to consider, negative eigenvalues we do not need to consider. Last one is if lambda is in fact 0. We then would end up with y double prime equals 0. How do I solve this? Yeah, just integrate. So this will give me y prime equals c1. Integrating again, y equals c1x plus c2. If we consider y of 0 equals 0, we get 0 equals c2. If we consider y of pi equals 0, we get 0 equals c1 times pi. Again, c1 equals 0. This is good. That tells us that there are, again, no non-trivial solutions. So lambda is not going to be equal to 0. Okay, keep going. It's going to require me to flip the page. No. Okay. So, here's what we learned from doing all that work. If we consider the boundary value problem, y double prime, add lambda y equals 0, with the boundaries y of 0 equals 0 and y of pi equals 0, this boundary value problem has an infinite sequence of positive eigenvalues we write it as lambda of n equals n squared, where n is 1, 2, 3, etc. So before we used mu. And the corresponding eigenfunctions are proportional to sine of nx. So that was what we found in the first case. No other real eigenvalues. So in other words, when the eigenvalue is negative or 0, are going to give us non-trivial solutions. There, though, could be complex eigenvalues. So we're going to do one last example, and then that'll be it for notes. Boundary value problem is y double prime, add lambda y equals 0. The conditions this time, y prime of 0 equals 0, and y prime of L equals 0. We are going to find the eigenvalues and eigenfunctions.
Is this considered homogeneous?
Yes. Okay, so we already said the only case we need to consider is that when that eigenvalue is positive, in which case we let lambda equal mu squared, just so that it's easier to solve. We then get y double prime add mu squared times y equals 0. We look at the auxiliary equation, we're going to end up with m equals plus or minus I times mu. Y then is c1 cosine of mu x, add c2 sine of mu x. In this case, our boundaries have to do with the derivative of y. So before we find those constants, we're going to have to find the derivative. It's going to be negative mu c1 sine of mu x, add mu c2 cosine of mu x. So if we start with y prime of 0 equals 0, that's going to give us 0 equals negative mu times c1. Sine of 0 will be 0, plus mu times c2 cosine of 0. So this gives us 0 equals 0 plus mu times c2. We already said, though, that our eigenvalue can't be 0. That would be trivial, which gives us c2 equals 0. We also have y prime of L equals 0, in which case we get 0 equals negative mu times c1 sine of mu L. We don't want mu to be 0. That would be trivial. We don't want c1 to be 0. That would be trivial. So we want sine of mu L to be equal to 0. Okay, sine is equal to 0 at n times pi. And this is for n is 0, 1, 2, etc. Bless you. This gives us mu is equal to n pi over L for n equals 0, 1, 2, etc. That means then that our eigenvalues, the Zach?
So we're saying that C1 is trivial now because C2 was 0 before?
Correct. So we don't want the case where both are 0. Okay, so how does this help us? It helps us find the eigenvalues for which we have non-trivial solutions. All the way up here we said lambda was equal to mu squared. If we have mu, that means our eigenvalues are n pi over L squared when n is 0, 1, 2, etc. Those are the eigenvalues. Our eigenfunctions then. C2 I'm going to choose to be 0. Or 1 rather.
Sorry. Again, we said mu wasn't equal to 0, and then we were saying that mu can be 0 with the eigenvalues.
Oh, then we need to start at 1.
Just start at 1.
Yes. Thank you for pointing that out. Okay, so then C2 is arbitrary. Our solution ends up being sine. Nope. C2 is 0, so cosine of mu x. So this will be cosine of n pi over L x. And then any constant multiple of that will also be a solution. Rachel?
Why does the first equation have the squared for the lambda, then we don't use the squared?
So here, this comes from here. Lambda is equal to mu squared. This comes from our solution.
Oh.
Helen.
Where does the n pi come from right below the sine UL? Where because UL equals 10 pi.
The only place that sine is equal to 0 is at multiples of pi. Anything else?